Connecting a 4 American wire gauge conductor to a rebar electrode requires careful consideration, primarily focusing on the rebar size. The National Electrical Code mandates a listed and approved connection method, such as a mechanical or welded connection. Let's explore these options. For mechanical connections, specifically when dealing with 1/2-inch rebar, a copper crimp lug rated for a minimum of 4 American wire gauge can be utilized. This connection is secured with a bolt or screw appropriately sized for the lug. When the rebar exceeds 1/2-inch, it becomes necessary to employ a larger crimp lug along with a correspondingly larger bolt or screw. It is important to emphasize that the specific sizing of the lug and the bolt or screw should always adhere to the manufacturer's recommendations. These recommendations are crucial for ensuring a safe and effective connection. Now let's move on to welded connections. For both 1/2-inch and larger rebar, a welded connection offers a viable alternative. This involves using a welding rod that is compatible with the rebar material, along with a welding torch. Similar to mechanical connections, the welding process should be executed in accordance with the manufacturer's recommendations. The weld itself must be of sufficient quality to ensure a permanent and reliable connection. Determining the proper connection size involves a few key factors. Firstly, rebar size. The rebar size serves as the primary determinant for the minimum size of the mechanical connection, or it dictates the correct size of the welding rod needed for a welded connection. Secondly, conductor size. The connection needs to effectively accommodate the 4 American wire gauge conductor. Thirdly, strength. The connection must possess adequate strength to withstand potential forces such as tension or bending. Finally, corrosion resistance. It is vital to construct the connection using materials compatible with the rebar and that exhibit resistance to corrosion over time. Regarding rebar length, exceeding 20 feet doesn't automatically necessitate an increased connection size. Only when the rebar is larger than 1/2-inch does the connection size need to be adjusted. The length of the rebar, assuming a proper connection, does not affect the required connection size. Now let's dive a little deeper into mechanical connections. When selecting a mechanical connector, consider the material compatibility between the connector, the copper conductor, and the steel rebar. Galvanic corrosion can occur when dissimilar metals are in contact, especially in the presence of moisture. Look for connectors that are specifically designed for direct burial applications, as these are typically made of materials that are resistant to corrosion. The connector should also be listed for the specific wire size and rebar size being used. The listing ensures that the connector has been tested and meets industry standards for performance and safety. During installation, make sure that the surfaces of both the conductor and the rebar are clean and free of any dirt, rust, or other contaminants. These contaminants can interfere with the electrical connection and reduce its effectiveness. Apply an appropriate antioxidant compound to the surfaces before making the connection. The antioxidant compound helps to prevent corrosion and ensures a good electrical contact. Tighten the connector to the manufacturer's specified torque. Over-tightening can damage the connector or the conductor, while under-tightening can result in a loose connection. Use a calibrated torque wrench to ensure that the connector is tightened to the correct torque. After the connection has been made, inspect it carefully to ensure that it is secure and that there are no loose strands of wire or other signs of a poor connection. Periodically inspect the connection over time to ensure that it remains in good condition. Corrosion, vibration, and other factors can loosen the connection over time, so it is important to check it regularly and retighten it if necessary. Moving on to welded connections, welding the 4 American wire gauge conductor directly to the rebar is another option, but it requires specialized equipment and expertise. The welding process can generate a significant amount of heat, which can damage the conductor or the rebar if it is not done properly. The welding rod used must be compatible with both the copper conductor and the steel rebar. The welding rod should also be listed for the specific application. Before welding, clean the surfaces of both the conductor and the rebar thoroughly. Remove any dirt, rust, or other contaminants that could interfere with the welding process. Use a wire brush or other abrasive tool to clean the surfaces. Use a welding technique that is appropriate for the materials being joined. The welding technique should also minimize the amount of heat that is generated. Allow the weld to cool slowly after it has been completed. Quenching the weld with water or other cooling fluids can cause it to crack or weaken. Inspect the weld carefully after it has cooled. Look for any signs of cracks, porosity, or other defects. If any defects are found, the weld should be repaired or redone. Protect the weld from corrosion after it has been completed. Apply a coating of paint or other protective material to the weld to prevent it from rusting or corroding. Regardless of whether a mechanical or welded connection is used, it is important to follow all applicable codes and standards. The National Electrical Code provides specific requirements for grounding and bonding, and these requirements must be followed to ensure the safety of the electrical system. In addition to the National Electrical Code, there may be local codes and standards that apply. Check with the local electrical inspector to determine what codes and standards are in effect in your area. The authority having jurisdiction, or AWG, is responsible for enforcing the National Electrical Code and other applicable codes and standards. The AWG has the authority to approve or disapprove of electrical installations, and it is important to work with the AWG to ensure that the installation meets all applicable requirements. Now consider the specific application. The size of the connection between the 4 American wire gauge conductor and the rebar electrode will depend on several factors, including the size of the rebar, the type of connection being used, and the environmental conditions. In general, the larger the rebar, the larger the connection that will be required. Also, welded connections can typically handle higher currents than mechanical connections, so a smaller welded connection may be sufficient in some cases. If the rebar is exposed to corrosive elements, such as salt water, a corrosion-resistant connection will be required. The connection should also be protected from physical damage, such as being struck by vehicles or equipment. In addition to the size and type of connection, the quality of the connection is also important. A poor connection can result in high resistance, which can lead to heat buildup and even fire. Make sure that the connection is properly installed and tightened, and that the surfaces of the conductor and rebar are clean and free of corrosion. Regular inspection and maintenance of the connection are also important. Check the connection periodically for any signs of corrosion, damage, or looseness. If any problems are found, the connection should be repaired or replaced. Keep in mind that the National Electrical Code Section 250.52 A3 outlines the requirements for concrete-encased electrodes. This section specifies that the electrode must consist of at least 20 feet of one or more steel reinforcing bars or rods of not less than 1/2 inch in diameter, or of at least 20 feet of bare copper conductor not smaller than 4 American wire gauge. The reinforcing bars or rods must be encased by at least 2 inches of concrete and must be located within and near the bottom of a concrete foundation or footing that is in direct contact with the earth. The purpose of the concrete-encased electrode is to provide a low impedance path to ground for fault currents. This helps to protect people and equipment from electrical shock hazards. It also helps to prevent damage to electrical equipment from overvoltages. The concrete-encased electrode is typically used in new construction, but it can also be used in existing buildings. If the building has a concrete foundation or footing, the reinforcing bars or rods can be used as a concrete-encased electrode. If the building does not have a concrete foundation or footing, a separate concrete-encased electrode can be installed. The concrete-encased electrode must be connected to the building's grounding system. This can be done by connecting a grounding electrode conductor from the electrode to the building's main grounding bus bar. The grounding electrode conductor must be sized in accordance with the National Electrical Code Table 250.66. The grounding electrode conductor must also be protected from physical damage. This can be done by running the conductor in conduit or by using a listed and approved cable assembly. Remember that concrete-encased electrodes are an effective way to provide a low impedance path to ground for fault currents. By following the National Electrical Code requirements for concrete-encased electrodes, you can help to ensure the safety of people and equipment from electrical shock hazards. Let's recap on the importance of proper grounding. Proper grounding is essential for electrical safety. It provides a path for fault current to flow back to the source, which causes the circuit breaker to trip and to energize the circuit. This helps to prevent electrical shock and fire hazards. Grounding also helps to protect electronic equipment from damage caused by overvoltages. There are several different types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. The type of grounding system that is used depends on the application. The grounded system is the most common type of grounding system. In a grounded system, one of the conductors is intentionally grounded. This provides a low impedance path for fault current to flow back to the source. The ungrounded system is used in some industrial applications. In an ungrounded system, none of the conductors are intentionally grounded. This makes it more difficult for fault current to flow back to the source, which can reduce the risk of electrical shock. The impedance grounded system is used in some high voltage applications. In an impedance grounded system, an impedance is connected between the neutral conductor and ground. This limits the amount of fault current that can flow back to the source. In addition to the type of grounding system, the size of the grounding conductor is also important. The grounding conductor must be sized large enough to carry the maximum fault current that could flow back to the source. The size of the grounding conductor is specified in the National Electrical Code Table 250.122. The grounding conductor must also be properly installed. The grounding conductor must be connected to the grounding electrode and to the equipment grounding bus. The grounding electrode is a metal rod or plate that is buried in the ground. The equipment grounding bus is a metal bar that is located inside the electrical panel. Proper grounding is essential for electrical safety. By following the National Electrical Code requirements for grounding, you can help to ensure the safety of people and equipment from electrical shock and fire hazards. In summary, when connecting a 4 American wire gauge conductor to rebar, remember that rebar size dictates connection size. Use listed connectors, apply antioxidant compounds, and follow torque specifications. For welding, use compatible rods, clean surfaces, and inspect welds thoroughly. Adhere to the National Electrical Code and local codes. Consider rebar size, connection type, and environmental conditions. Ensure a quality connection to prevent heat buildup. Concrete-encased electrodes, as per National Electrical Code 250.52. A3 require at least 20 feet of 1/2-inch rebar or 4 American wire gauge copper. Always prioritize safety and proper grounding techniques. The connection must also be strong enough to withstand the forces that may be applied to it, such as tension or bending. The connection must be made using materials that are compatible with the rebar and that will not corrode over time. If the rebar is longer than 20 feet, it is not necessary to increase the size of the connection unless the rebar is also larger than 1/2-inch. The length of the rebar does not affect the required connection size as long as the connection is made properly. The National Electrical Code (NEC) requires that the connection be made with a listed and approved method, such as a mechanical connection or a welded connection. For a 1/2 rebar, a mechanical connection can be made using a copper crimp lug rated for a minimum of 4 American wire gauge and a bolt or screw that is sized for the lug. For a rebar larger than 1/2, a larger crimp lug and bolt or screw will be required. The size of the lug and bolt/screw should be determined in accordance with the manufacturer's recommendations. For both 1/2 and larger rebar, a welded connection can be made using a welding rod that is compatible with the rebar and a welding torch. The weld should be made in accordance with the manufacturer's recommendations and should be sufficient to ensure a permanent and reliable connection. The proper size of the connection can be determined by considering the rebar size, the conductor size, the strength, and the corrosion resistance. The size of the rebar will dictate the minimum size of the mechanical connection or the proper size of the welding rod. The connection must accommodate the 4 American wire gauge conductor.